And so in this video, we're going to talk about osmosis and osmotic pressure. One important key topic that we need to talk about before we jump into osmosis is the idea of certain materials are semi-permeable. All right. So what does this mean for something to be semi-permeable? All right. So for example, we have a sponge, right? So this is this is a really ugly sponge, really. All right. So this is my take of a sponge. Okay. So sponges have holes, rigids, whatever. Look like ugly cheese. But the point is that a sponge is semi-permeable. It allows only certain things to pass through and other things cannot. So like for example, if you were to, put water, right? Water is allowed to pass through a sponge or any type of liquids really, right? So it could go through sponge. While you may have like things like dirt and grime, all right, cannot pass through a sponge and it will stay on the surface. So thus a sponge is semi-permeable. Okay. Now, when it comes to biology and the ideas of things that's sustainable for life, this semi-permeable function is really, really important. So like cells, the things that make up all living creatures, right? Most cells, they have a membrane that's also semi-permeable, and it allows the transfer of solutes and solvents to pass through the membrane, and that way the cell could use it accordingly. So like for example, if this is the membrane itself, it has tiny little pores. All right, so if this is the tiny pores, here are some particles, right? And here's some other particles here. All right, it allows that particles could move back and forth between this membrane here. All right, and so that way the cells could either take in food this way, it could excrete out waste this way. All right, it's all in just to make sure it can maintain homeostasis, right? Balance. All right, now when you have the movement of solvent, right, in this case water, across the I can't even spell across correct. Movement of water through this membrane, right? And so what we have here, through the semi-permeable membrane, if you have a movement of water or solvent through this membrane here, all right, this process is what we call osmosis. All right, so it's this movement of water, and it allows the cell to take in water and all the nutrients that it possibly may need. Okay. Now, so how does this work? So typically, this diffusion or this movement of water takes place when there's a higher concentration of water on one side, and a lower concentration of water on another side. And so when this takes place, then water will flow from areas where there's a high concentration of water to a area where there's low concentration of water. All right, and so for example here, if this is your membrane here, all right, and then kind of catch what I'm saying. So make sure you're with me on this one. So if you have your membrane here, right, and so let's just say that on this side you have 15% of some type of solute, all right, and on the other side you have, let's say, 30% of some type of solute. Okay, and so this is just the concentration. If this is the case, then here there's 85% of the concentration is water because the solute is dissolved into water, and here there's a 70% concentration of water on the other side. And so if that's the case, wherever there's a higher concentration of water, water's going to flow, or the solvent's going to flow towards that direction. All right, so in this case, then we expect that the osmosis, the process of osmosis, that water is going to flow mainly this direction because there's a higher concentration of water here and is going to an area where there's lower concentration of water. Now, as this is taking place, you have water that's pushing towards this direction, so because there is a higher concentration here versus here. All right, as water's pushing towards this direction, what's going to happen? It's going to collide more with the solutes that is here, causing an increase in pressure to the point where, because due to the increase of the pressure, the solutes will start moving across the membrane, right? And this will continue to take place until there's a reaching the equilibrium between the movement of water back and forth. All right, and so it's going to push this way. All right, and this increase of pressure, we call this osmotic pressure. All right. Now, osmotic pressure oftentimes has the symbol of a pi, all right? And this also can be calculated qualitatively. So, whereas pi, the osmotic pressure, is the moles over the volume times a gas constant, all right, times T, okay? And so this is basically a derivative of the ideal gas laws, all right, gas law equation. All right. And so osmotic pressure is also a colligative property. So this simply means that it doesn't matter what substance it is or the identity of the solute, but what matters is the concentration of the solute that affects the pressure. All right, and so we give it its own little unit. All right, and the unit that we give it to measure osmotic pressure, we call it osmolarity. Okay, or osmol. Okay, and basically it's osmol per liter. So that's what osmolarity is. Okay, now osmolarity, it's the moles of the particles divided by the liters of solution. And so to kind of give you an example of how this works, like, so for example, if you have like 0.2 molarity of concentration of glucose, this also equals 0.2 osmol per liter. All right, so the osmolarity of glucose will also be 0.2 moles, right? Or 0.2 osmol per liter. But if you have, like, for example, for example, if you have 0.2 molarity or molar of NaCl, well, this will equal 0.4 osmol per liter. Why is that the case? Well, NaCl, this ionic compound, we know that it deionizes when it's dissolved into water, okay? And it did not ionizes to Na plus and Cl minus, all right? And so what you have here, if you consider this whole concentration and the solution, what's going to happen is that really you make 0.2 molars of sodium ions and 0.2 molar solution of chloride ions. So these two together makes it that there are 0.4 osmol per liter, because remember, osmol or osmolarity, we're looking at the number of moles of dissolved particles, either ions or molecules, per liter of solution. Okay, and so 0.2 mole of NaCl will equal to 0.4 osmol per liter. Okay. So now, due to osmosis, there are three, specific conditions that a cell could be in depending on its surroundings, right? And so, for example, if, let's just say, for example, the osmolarity of a cell, of a living cell, is typically about 0.30 osmol per liter. So this is the osmolarity of a cell. Okay. Now, if the cell was placed into a saline solution, right? So sodium chloride solution, that's roughly 0.15 molar. Okay. Which, remember, 0.15 molar, we're talking about sodium chloride. So this is roughly 0.3 osmol per liter. All right. Then we say that the cell is in an isotonic condition, meaning, so if this is my container, right, right? And this is the solution. This is my cell, all right? Within the cell, it's 0.30 osmol per liter, all right? The solution is also 0.30 osmol per liter. This condition is isotonic, all right? It's in the isotonic condition, okay? So this simply means that the concentration within the cell and the concentration outside the cell are exactly the same, and the cell overall will not be harmed, okay? So there's not going to be a change or a fluctuation in which way the water is going to be going. Now, versus if we had in a container, right? And so within the container, we have a solution. Let's say the solution, right? It had osmolarity of 0.10 osmol per liter, right? Our cell still has a 0.30 osmol per liter. All right, what's going to happen? Well, there's a difference in concentrations, okay? And so because there is a difference in concentrations here versus here, then we know there's going to be some movement of water, all right? And a net movement of water specifically. So how do you determine which direction the water is going to move, right? Is the water going to move from the solution, from the surrounding to the inside the cell, or is it going to move the opposite direction? Remember, it's all about which side has the high concentration of water. All right, and so what we find here that this solution has a higher concentration of water because the solute concentration is just 0.10 osmol, while within the cell it is 0.30 osmol. So the concentration of water is outside the cell is much higher. And so what's going to happen, the water is going to flow into the cell. All right. At this point, then we say that the cell is in a hypotonic condition, or is in a hypotonic solution. Okay. So then that's when there is a less concentration of the solute outside in the surroundings versus what's in the cell. Okay. Now what's going to happen? It's the cell is going to undergo what we call hemolysis. Now hemolysis is basically when the cell swells due to the influx of water. All right. So there's water entering in the cell much more quickly than it's leaving the cell. And so the cell is going to ultimately swell up. All right. It's going to undergo through a process what we call hemolysis. And then oftentimes it could potentially just burst as well. Okay. Now the last condition, all right, it's the opposite. So let's just say we have a solution here, and within the solution, it has a osmolarity of, let's say, 0.50 osmol per liter. Our cell here is still 0.30 osmol per liter. Okay. Now what's going to happen? Well, same idea. Wherever has more water, it's going to leave to the area that has less water. And so when it's due to this, just the concentration, well, we find that the water is going to leave the cell. All right. Now, when this happens, we said that the cell is in what we call a hypertonic solution, or is in a hypertonic condition. All right. And because it is in a hypertonic condition, the cell is losing water. The cell ultimately is going to shrink and shrivel. All right. And this process is what we call crenation. All right. So the cell's crenating, or it's undergoing crenation, where it starts shriveling and shrinking due to the loss of water. Okay. And so that's what we have for osmosis.